Hello and good morning to the presentation from Team Goodwin on ACDS Task 3 Wildfire. Before we start, we'd like you to meet our wonderful team that's contributed really well to this project. And so this is us. Hello. Now, let's start with a quick introduction on why we want to do this, the motivation behind what's happening. So over the last week, we've curated some of the news that's come over regarding the wildfires across the globe. The first one in Canada, where some 6,000 people were told to evacuate in Alberta. The second one, there's now a fire in Arizona with around 5,000 acres. This was by the Independent, the previous one was by the BBC. And the third one is that 600 million in EU funds have been allocated for firefighting equipment. And this was by the European Commission, directly from the source. And this is all just in the past 4 or 5 days. So you can see how big of a problem wildfires have become. So let's look at the impact of wildfires in a snapshot. On the left, we took this photo on 21st May, and this is basically a screenshot from the ESRI, the Environmental Systems Research Institute, that shows current wildfires. Now, the yellow you see correspond to more intense wildfires, so the one we discussed in Canada, Arizona, and a couple more in Southeast Asia and Russia. 339,000 people are killed both directly and indirectly due to wildfires every single year. Now, 50 billion is the annual cost incurred due to all of these wildfires every year, and 7.5 million acres were lost in the USA alone in 2022. So we've got the sources below if you'd like to go through them. And so the need to act and prevent wildfires and to protect people from the impact of these is right now. And we can leverage AI to really help with this task. There's 4 ways we can do this. Early detection. By identifying where wildfires can happen, we can almost prevent them from happening in the first place. Predictive modeling. Again, identify patterns where these are happening and identify potential regions where this could happen. Resource allocation. When there is a wildfire, how do we optimize resources to go and quell the fire and save people? And risk assessment. How big of an impact would any wildfire cost? So here's a quick look at our GitHub file structure. And this doesn't include all of the documentation, it's just the main pieces of code for your perusal. So we've got data. Now obviously we've left it empty because we don't want to upload large files to GitHub. And then in notebooks, we have tasks 1, 2, and 3. Now all of these extract data from the folder, so you would have to load the data into the folder if you want to play around with this. Then we have the SRC, which has in it the datasets which contain loading the datasets, models that contain the models, predict, to obviously predict the output images, and the training and utils, so those random seeds and things like that are found in utils. And then we've got a couple of test files to really test whether our code is working or not. You can use them to test if the code successfully executes on your system. We also have the objectives.pdf and requirements that were given before. And requirements is just to understand the libraries you need and the versions.
So let me introduce the model we used in the first task. We used the RNN surrogate model to predict a wildfire image. And at first, we wanted to use PCA to train the data and then use LSTM to predict the image because it was more efficient. But we found the result was worse, so we move on to the other methods. Then we began task 1 by dividing into 2 teams, one focusing on prediction with an RNN and the other on LSTM networks for image prediction. We explored both types of recurrent networks and find the images with LSTM have better performance. As you see, with simple CNN and simple LSTM, we can get a dissatisfying result with high efficiency and short sequence. So the last model we used was CNN LSTM model, simple but we use CNN to process the image and then use LSTM to predict the next image. Here we choose a time series with a length of 4 and a time interval of 10. And we also use some hyperparameters and we use the sliding window technique to make the sequence. pooling, then finally using the dropout to get the convolution box. And for the linear layers, we just use the leaky rule activation function to get the linear box, and then applying it to the LSTM and to reshape them. And this is our housings to get the final image. And our detailed models are on this picture. So in CN model, we used 4 curved 2D layers with stride equal to 1 in combination with max pooling layer of stride equal to 2 to capture the spatial information of input data better. We use dropout layers to counter-model our fitting. We use batch normalization in the convolutional model to stabilize and speed up the training process. We use leaky ReLU to prevent vanishing or unmanaged gradients. And in LSTM model, we use layer normalization since recurrent networks work better with layer norm instead of batch norm. And then the number of layers in LSTM are 3. And then we combine the 2 models together and output the result by using sigmoid function. So as you see on the right, the CN LSTM has good performance with best MSE. So we're finally using these models in task 1.
Thank you so much for that. We'll now move on to generative surrogate models, which was task 2. And so we begin. So for the exploration, we mainly looked at GAN and VAE. We thought diffusion was a little overkill for this. So when we looked at GAN, the pros were we have very realistic samples as we saw in the deep learning module, which means it's great for complex natural phenomena like these. And unsupervised training on unlabeled data is a huge tick here because it only needs the distribution of real data, as you can see there. But when it came to VAEs, which generate samples from the probability distribution of the latent space, we got a very good diversity. It's more stable, of course, than a GAN, and it has better reconstruction capabilities. So when we looked at the pictures, and when we looked at the MSEs, VAEs significantly outperformed GANs, which is why we went with this. So if you look at the loss metrics, we tried MSE, but over that we preferred a binary cross entropy plus a beta, a factor, times scale divergence. And this is the industry standard, and although we played around with an MSE, we realized this is the industry standard for a reason. When we look at the inputs and outputs, because our satellite data is 10 time frames instead of 1 time frame with respect to the training data, we trained it so that the 0th image predicts the 10th image. The first image is used to the 11th, and so on. So the final model, as mentioned before, was a convolutional VAE. We put shuffle equals true for training, batch size of 32, epochs of 10. You can see the learning rate, wave decay, and the beta factor. Now, these were the hyperparameters we choose after a lot of testing and playing around, and these are the final results. So, we've seen a couple of building blocks already. Let's look at a few more. When you take a deconvolution, mix it up with a batch normalization, a Ricci-Lelio activation, a dropout, you get one secret box. And then when you take a linear layer with an activation of ReLU, you get an open linear box. And a deconvolution with the sigmoid activation, we like to call something as a small open lock. Now let's look at the encoder real quick. So when you pass an image, it goes through 4 sets of convolution, reshaping, and then it goes through a linear layer, and 2 separate linear layers to get mu and log y, which is basically an extension of sigmoid, which is more stable. So this is the encoder. And then when we take the latent space, what makes the VAE variational is that we take that sigma or the log var and multiply it with random noise, which gives us reparameterized latent space. This makes the autoencoder more robust and better. Looking at the decoder, we have the reparameterized latent space, 2 linear sets. We have the reshaping and 3 sets of deconvolution, final deconvolution with an activation, and the output image, which is the decoder. So the final VAE has an encoder with 2 things combined to get a reparameterized decoder and the final image. So in the interest of time, we're going to just pause here for a second and you can go through all of this. But the thing we want you to know is that we clip the model's gradient to make sure that there is no exploding gradient or constant overshoot. When we look at the model results, this is the VAE input. This is the target, which is the 10th time frame. And then we have the difference between the input and the target. and then the VAE generated images, and the differences between the generated and the target. So when you look at these, you can see how remarkably well our model performed.
All right, moving on to task 3, which was data assimilation. For data assimilation, we have some background model data, we have some sensor data. We multiply each with their respective covariance matrices, and then we mix them together with a factor of h, and we have some assimilated data to hopefully improve the result. For the time step of the training data was delta t of 1, but for the sensor data and the background data that we are using for data assimilation, we're going to take, the delta t was 10, so we're going to take the 0th and 10th image of training data to train the models. These are our given data. For the task 1 model, we used the first 4 images to predict the 5th image, and we used, for task 2, we used the 4th image to predict the 5th image so that we would be predicting the same image. So you can see here. We ran into a problem when we were calculating the covariance matrix, that we have a single input vector, but the covariance of requires multiple vectors, and it ends up with a division of 0 by 0 because one of the parameters is the number of samples minus 1. So we did try using the one sample, but it ended up with really bad results. Our solution was to pass a 300 element array and treat each principal component as an individual vector for the covariance matrix calculation, as you can see here. You can see in the middle here that we tried calculating the covariance matrix with 5 images, and these 5 images were the background data that were given, and they didn't really bear any relationship to the models that we had. So you can see that they gave a really bad result and a high MSE, but using our improved method, using the 300 vectors, we obtained a very good result for task 1 and task 2 with a very low MSE.
Thank you so much for that. Now let's just have final thoughts on our project so far. We've got testing, we've got really good testing. We use PyTest to make sure that you can check the functionality of the code once you install our package. And we also use things for easy documentation. When it comes to what we could have tried with more time, when it comes to the models, we could have used a VAE-GAN combination. Now this is state-of-the-art research going on where we can take the VAE to be the generator part of the GAN to get better outputs. So you get the sharpness of the GAN with the variability of the VAE. And when it comes to the data, we could have tried to consolidate more data online or to create perhaps synthetic training data. And on the other side of things, we could have tried using pre-trained network weights and using grid search for hyperparameters in a more detailed fashion, but due to time, we couldn't really get onto that. With that being said, thank you so much for your time and for tuning into our channel. Thank you so much from Team Goodwin.